Our device was made by using a water bottle as the housing. In it, there are two filters secured at the bottom and top by rubber bands and an activated carbon placed on top of both of the filters. In order to be cost efficient with our housing, we cut off the bottom of the plastic bottle and inverted it. 3 tongue depressors were then taped onto the housing to allow it to hang over and drip into the paper cup for collection.
While designing our filter, our main goal was to primarily keep it inexpensive. We decided to focus on cost because of the 10 cheapest filters stretch goal. We started with the basic idea of vertical housing, filled with a medium and a filter at the bottom. We then looked into ways to cut costs on that basic idea. We began ordering the cheapest variant of each part we would need, so paper cups, coffee filters, cheap coarse sand, etc. We figured we would start with the cheapest, lowest quality options, and if those didn't work for whatever reason, we would upgrade them, which is exactly what we did.
The cost of materials is as followed. Tape, $10. Cotton ball, $1. Plastic bottle, $20. Cheesecloth, $15. 2 rubber bands was $1 each, so $2 total. Tongue depressors were $3 each, so $9 total. Activated carbon was $35. The paper cup was $1. The total cost was $93.
While our flow rate was sufficient, taking only about 60 seconds to collect the required 10 milliliters of water, our filter did not perform well in dye removal. Through our Arduino photometer, we calculated about 91.1% absorbance by the filtered water, while the spectrometer provided to us gave us an absorbance of about 90.4%. Comparing these values to the calibration curve gives us an estimate of removing only about 25% of the original dye. The graph shown shows light absorbance as a function of the concentration of dye in water. In this case, the concentration is measured in percentage of the original mixture, while the light absorbance is measured in the percentage of light absorbed compared to that of the original mixture. We collected 5 light readings with our spectrophotometer photocell through various concentrations of water, and used that to calculate absorbance. With those 5 data points, we created a basic calibration curve with an R-squared value equal to 0.9767. We then used this curve to evaluate the effectiveness of our filter. By plotting the absorbance of our official test on the curve, we see that our filtered sample has a concentration of approximately 75% of the original mixture, with a flow rate of about 1.66 milliliters per second.
Our general approach was to start with inexpensive variants and change to more expensive options if necessary. Our design iterations consisted of changing the medium and altering the device to best suit our needs. Since we wanted to make the device as cheap as possible, we began working with coarse sand and fine sand as our media. When testing both of these media, we discovered that their performance was abysmal. The coarse sand would completely dirty the water, and the fine sand merged together like wet cement. We then chose activated carbon as the alternative media, which proved to be a much more desirable flow rate and would not make the water filthy at all. Our next iteration consisted of making a design that would effectively cover the top of the open bottle as we poured water. This was necessary to slow down the water flow and to make it possible to add media to the top. Per our goal of making the design cheap, we initially used filter paper to cover the top. We soon discovered that the filter paper was far too weak and would rip after a certain amount of water was poured. Cheesecloth became the chosen alternative for this task. The advantage with cheesecloth is that it never rips and can hold a substantial amount of activated carbon on the top. Overall, this was a very intensive project. Given more time, we would create a filter that operates continuously from an external reservoir to fulfill another stretch goal. Since we were operating well under the budget, we could have easily spent more money to create this mechanism without hindering our progress.